Let's speak about modern geodetic equipment. Well, historically, we have used a huge amount of analog instrument for plan surveys. Land survey, engineering or construction surveys, and field mapping. The basic methods were location a point, measuring an angle, measuring a distance, measuring differences in elevation. Location a point, we have few main methods of location of a point, while start with known location of previous point. First of all, it's polar coordinates using direction by bearing, using direction by angle, and station and offset while using right angle of 90 degrees. Another option is direction plus distance, common for plan surveys. While using two reference points, we can locate a point with while measure directions by bearing, directions by angle, or position of unknown point with two distances. And method number 3, direction from one point, distance from another point. This also possible method of location of a point. We use a huge amount of instrument for measuring an angle. First of all, different theodolites. We know how to measure horizontal angles. We use level, transit, or theodolite. A vertical angle, we use transit or theodolite. And also can use graduated circle or digital readout. Horizontal and vertical circles typically graduated to 1 degree for construction grade instruments, 5 minutes or better for survey instruments. Ancient equipment vernier improves resolution by 10x or better. Here you can see vernier measurement equipment. Measuring a distance while starts with known location or previous point, we have 3 techniques. First, taping. We can use tape or chain and physically measure the distance between points. Stadia markings. We can calculate the number of centimeters on the road, and then we can calculate the distance between instrument and road. because this upper and lower crosshairs. And the last one method is electronic distance measurement in our modern precise instruments. While using typing, we have kind of problems or errors how to align our tape tension while we can use this tension is different on different surfaces, on the grass, on the concrete, on the asphalt, etc. Thermal expansion of the tape or the chain, we can use correction tables, and while measuring the distance on a slope, we can use trigonometric formulas or cosinus, sinus, etc. Stadia markings and rod. Stadia markings is with vertical tangent screw rise telescope until lower stadia hair is 4.0. The upper stadia hair will be 4.29, and the stadia intercept is still 0.29, but easier to determine. Stadia hairs has, while we observing a rod through the crosshairs, the stadia hairs makes the permanent angle, and intercept equals 1 to 100 of line of sight distance within the transit, and this ratio holds true for extensions beyond the transit. If we have 1.22 feet from the between the stadia hairs, we just need to multiply the 1.22 to the 100, and then we can get 122 feet from the instrument center to the rod. The stadia markings and rod, this method is not very accurate, but much faster than measuring with taping or chaining. And the last one, electronic distance measurement, sometimes optical, sometimes it's not very precise, sometimes ultrasonic, mid-priced, and not very big accuracy. And the laser one, moderate to very expensive accuracy, is very good. Here you can see example of pocket geodetic equipment that allows to measure distances in the room on the construction place with big accuracy. Well, measuring elevations, also known as leveling, uses a level optical or ladder and rod, or measurements are relative to a starting elevation. And here you can see the short explanation of the geometric leveling. Optical leveling requires at least two workers. Laser leveling can be done alone, but easiest when rod is equipped with auto detector. That we have seen this auto detector in the second video from our Illinois colleagues. So this laser auto detector can find itself the highest signal level, and so we can measure, we can read the reading on the rod. Well, while putting all these methods together, we can use for at least two ways of region mapping. Traversing uses to locate specific features. Traverse mean measuring the angles and distances, angles and distances, angles and distances. And triangulations uses to establish controlled network over a region. And another option of triangulation use is so-called bridge triangulation, where we constructing a bridge across a river. We use special so-called bridge triangulation, which is very precise and accurate, and we can use it very good. Another option is very rare. It's trilateration, when we measure triangles, the distances, every distance in every triangle. Here you can see types of traverses: first class, second class, and third class. This an example of closed loop traverse, closed connecting traverse, and open traverse. What does it mean closed connecting traverse? It begins from the known stations and then it ends at the points with known coordinates. Open traverse only begins from known station and then goes not very far, but to the unknown area. Well, the total station combines theodolite and electronic distance measured, data logger, and surveying software. It can log at least 8,000 points, download data to computer, well, total stations are very precise, and then we will speak much more about this modern equipment. Well, a short history of length measurement. Here you can see a theory of how can we have at least two methods of diffractions measurements. We can measure the time moments of time difference between force and back impulses that go through the distance between the instrument and reflector. And we use tachyometry just as a system of rapid surveying by which the horizontal and vertical positions of points on the Earth's surface relative to one another are determined without using a chain or tape or a separate leveling instrument. Instead of the pole formerly employed to mark a point, a staff similar to level staff is used. It is marked with heights from the base of foot and is graduated to the form of tachyometer in use. We can here we can see the different ancient stadia measurements. We have spoken about it. Substance bars. It's also ancient device that nowadays is not used at all. Substance bar. It's a right rod, usually a material insensitive to change in temperature, such as in var, or fixed length, typically 2 meters. This bar is mounted on a tripod over the station to which the distance is desired. And nowadays, the first right equipment, radioelectronic equipment, was tellurimeter. It was the first successful microwave electronic distance measurement equipment. The name derives from the Latin tellus, which means the earth. The original tellurimeter, known as microdistancer, was introduced in 1957. It's very, very long ago. It was invented by Trevor Wadley of the Telecommunication Research Laboratory of the South African Council for Scientific and Industrial Research. He was also responsible for the wide loop receiver, which allows precision in turning over wide bands. The principle of the tellurimeter emits a microwave frequency radio wave. The remote station carries a transponder that radiates the incoming wave in a similar way or more complex modulation. The resulting phase shift, you can see the phase of an electromagnetic wave, is measure of the two-way distance traveled. The results appear on a cathode ray tube with circular sweep. Well, nowadays the radio equipment also used in geodesy. However, most of all we use laser equipment which use laser beam to determine the distance to an object. A long-range laser rangefinder is capable to measure distance up to 20 kilometers. Well, the calculation we calculate the time shift between the impulse goes out from the generator and then it reflects from the reflector and then goes in opposite way to the receiver. In this case, distance is equal to c divided by 2, where c is the speed of light and t is the amount of time for the round trip between A and B. These laser range meters, range finders are used in the military and in geodesy, in 3D modeling. This in sports, etc. Laser rangefinders are used extensively 3D object recognition. This kind of LiDAR equipment may be used to scan buildings, rock formations, etc., and to produce 3D model. The LiDAR can aim its laser beam in a wide range. Its head rotates horizontally, a mirror flips vertically. The laser beam is used to measure the distance to the first object on its path. And now let's move on. The total station is an improved version of modern surveying instruments such as electronic distance measurement, outer level and digital level. Total station is a combination of electronic theodolite and electronic distance meter. This combination makes it possible to determine the coordinates of reflector by aligning the instrument's crosshair on the reflector and the simultaneously measuring the vertical and horizontal angles and slope distances. Onboard microprocessor in the instrument takes care of recording readings and the necessary computations. The data can be easily transferred to a computer where it can be used to generate map. Here you can see principal schema of total station. We can measure the angle and distance to the object and calculate the 3 coordinates of the reflector. The total station works by firing an infrared laser beam at a reflector mounted on a stadia rod. The distance between the total station and the reflector is calculated based on the time taken for the beam to reflect back to the total station. Total stations were originally developed for the construction industry, surveying new roads, laying out buildings' foundations, utility lines, etc. You can see the different stages of an electronic distance measurement. Here you can see signal generation, signal pass, signal reflection, and backwards the signal uh, gets back to goes back to instrument. There are two main reflector properties that are not subjected to a measure of quality. The first is the reflection type and its general geometry. Is it a 360 reflector that reflects measurement signals from all directions, or does it require being aligned with the instrument's line of sight, such as the round prism? Second main reflector property is the reflector constant. The reflector constant is given property of the particular model. Here you can see different models of reflectors. They are made of metal. They all have different centering accuracy. And all they have different reflector constant that is given parameter while they manufacture this equipment. To define what the prism constant is, we must first explain how a prism target works. In principle, the target reflector is a piece of glass that bounces off the signal in the same direction it came from. The image shows how the incoming electronic distance measurement signal is reflected in the same direction it came from. Here you can see the example of total station work. The triangle point is a place of total station. Then we must orient it to the north. Mainly we use another control point to find the azimuths of the direction of our distance, and then we just measure the angle between the north and the distance from point where the total station is situated and where the measuring rod with a prism reflector with a target reflector is situated. Here you can see calculations. This calculation is very easy. Most total stations have the ability to record survey data as a digital file, which can be imported to a PC-based GIS program. We use total station in field work because the total stations is very fast. The second issue is that accuracy of measurement is high. Manual errors involved in reading and recording are eliminated. Calculation of coordinates is very fast and accurate. Even corrections for temperature and pressure are automatically made. Computers can be employed for map making and plotting counter and cross sections. Counter intervals and scales can be changed in no time. For mapping small areas, we use total stations. The range of total station is around 2 miles or so, assuming you have good lines of sight. A good example would be mapping an archaeological dig site. There are many other applications in earth science that requires great accuracy. For example, monitoring cliff erosion, glacier movement, changes in beach profiles, sand dune movement, construction, etc., etc., etc. Here you can see examples of different. This is the main transnational corporation that produce the total stations. Later I will show you presentations of the equipment that this corporation are manufacturing. First is a Trimble company. It's an American company from the United States. Another one is Leica Geosystems. Nowadays is part of Hexagon Corporation from Switzerland. And another one is Topcon Corporation. It is from Japan. Also, we have huge amount of different brands that are have similar parameters. The equipment made of these films have similar parameters. And another huge technology is GPS, Global Positioning System equipment. And I have not spoken about this equipment yet. So we can see in the table comparison of total stations and global navigation satellite systems. Well, total station makes indirect acquisition of 3D coordinates. It allows both horizontal and vertical accuracies that are comparable. It's very important issue because GPS equipment, the horizontal accuracy is better than the vertical accuracy. Then the accuracy depends on the distance, angle, and the used prism. Total station is more precise than GPS. It is satellite independent, so we can use it indoors, underground, it needed intervisibility between the instrument and the prism. In my opinion, it is disadvantage because the GPS equipment does not need intervisibility between stations, and daytime data collection. On the other hand, GPS equipment makes direct acquisition of 3D coordinates. The horizontal accuracy is better than the vertical one. It's not good issue because in geodetic works we should measure all coordinates with the same accuracy. The accuracy depends on the satellite availability, atmospheric effect, satellite geometry, multipass, and so on. Nowadays, GPS equipment is less precise than total station. The GPS equipment is satellite dependent, so in deep wood, in deep forest, near the high buildings, underground, indoors, the GPS equipment does not work. And the good issue is that visibility between the instrument, between the points, is not needed. And GPS, we can use GPS equipment day or night, 24 hours, 7 days a week, all over our planet, and it does not need any control points except visibility of a satellite system. Well, and the last one, one of the expensive equipment is a smart station. The smart station control points are not needed because it has a GPS antenna directly on it. No awkward traversing required. It consistent high accuracy. It completes quicker and traversing skills not required. The smart station is a combination of satellite receiver and total station. Nowadays, they have manufactured kind of a smart station 4-in-1. It's GPS receiver, total station, laser scanner, and photogrammetric station. Another issue is robotic total stations that allows the operator to control the instrument from a distance via remote control. While the operator moves in the field, the robotic total station follows him automatically and can make a measure. It's finding the reflector itself, and one operator can do all the necessary work with this robotic total station. This eliminates the need of an assistant staff member, as the operator holds the reflector and controls the total station from the observed point. Well,